Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting rotational kinematics equations. This is a follow-up to the lecture in Physics 2 in early March 2012. On screen you can see the sheet we've had on screen in class, the top half showing the translational concepts and terminology and definition formulas that you've been familiar with since Physics 1, and then the corresponding rotational concepts, definitions, and defining formulas. On the bottom half of the screen, you see additional formulas for translational motion that you learned in Physics 1, and which apply when the acceleration of your object stays steady. What I want to show you today is the way we can generate rotational equations for constant acceleration simply by starting from the translational equations. This will work because the concepts for rotation are the same concepts as we use for translation. It's just a matter of applying them to spin instead of to motion along a path. So we can take these equations which were derived from the definitions and generate equations for rotation by just substituting into the equations the corresponding rotational values. For example, on this first equation, we have the final linear velocity equals starting linear velocity plus linear acceleration times time. If instead of final linear velocity, we start with final angular velocity, then we can put in our equal sign. Instead of the original linear velocity, we can put in original angular velocity. Next, we'll have our addition, and then instead of linear acceleration, we'll need angular acceleration, which is represented with the Greek letter alpha. Finally, instead of the time from the original equation, well, there's no substitute for time, so the equation completes with the t for time. So this equation is a valid rotational version of the linear equation that we started off with. I'm going to suggest now that you pause the recording and generate an equation, a rotational equation that corresponds to the second translational equation that you see on screen. Okay, instead of the S for linear displacement, you should be using the delta theta for angular displacement. Then, of course, our equals. Next, instead of the linear original velocity, we have original angular velocity multiplied by time. And then we're adding on 1/2 times the linear acceleration. So we need 1/2 times angular acceleration, that's our alpha, and instead of time squared, well, once again, there's no substitute for time, so we'll be using time squared. That is our rotational version of the second equation. I'm going to suggest now that you pause the video again, generate the final two rotational equations corresponding to the final two equations on screen, and then restart to confirm what you have. So for the third equation, instead of linear final velocity squared, we're going to have angular final velocity squared. Next, the equal sign. Then, replacing linear original velocity squared, we have omega 0 squared for the original angular velocity squared. Next, 2 times acceleration, so that's 2 times alpha, And then instead of the S for linear displacement, we need angular displacement, which is delta theta. So that's how the third equation should work up. For the fourth equation, we're going to have, instead of linear average velocity, we will have average angular velocity. I think I'll use the bar over top to indicate the average this time. Then we have our equals, and then original velocity plus final velocity. So for the rotational version, original velocity is omega sub 0 plus final angular velocity is omega f. It's all going to be divided by 2. You want to be careful that when you're doing your average velocity equation that we just wrote out, that you remember to add the two velocities together, unlike in your equation for acceleration up above, where you subtract the velocities. Also, you want to watch out that when you're finding the average velocity, the equation we just wrote out, that you divide by 2 as opposed to the acceleration equation where you divide by t for time. I mention that because it's not unusual for people to kind of absent-mindedly put a 2 where they meant a t, or vice versa, or to mix the plus and the minus in these two formulas, because when you're saying these two formulas to yourself, they actually sound kind of similar. Thank you for joining me for rotational kinematics equations. I will be posting another video looking at a sample calculation using the relationships.